All right. So welcome back, everyone, to the NLP class. And I think this is a lecture 6. I just realized, right? So we are doing quite well. I asked back about A1, not so bad. And we already sneak peek on A2, and most of you also do quite a good job, right? So yay, bravo, right? So I'm very happy, and this is lecture 6, and there will be A3, right? So I will um, uh, maybe I should talk about A3 just slightly, and then we can jump to the lecture, all right? So for the A3, by the way, this is not the final version, but it should give you a rough idea what is A3, right? So in A3, what you have to do is machine translation. So for example, if you're from Vietnam, you translate Vietnam to English. If you're from India, you translate Indian to English. If you're from Thai, you translate Thai to English. Okay, so that is a basic idea of what this assignment is, right? Once again, this is purely based on a Jupyter notebook I wrote already from English to French, if I'm not wrong. Yeah, but I'm using a data set, right? Your task once again is try to find a data set that can help you translate from your native language to English, right? And this time you will also learn transformer, right? What you're gonna learn today, right? But you don't have to worry because I already finished all the code for you, right? So it's similar to A2. You just change the data set, debug a little bit because it's not always work. Tokenize the best way you can do for your language. Your language cannot use English tokenizer, right? Because your language should use your language tokenizer, right? So by doing all this, you will learn the nature of your language, right? And you will get a lot of knowledge by doing all this dirty work, right? So here I say that please describe in detail text normalization, tokenization, word segmentation. Basically, word segmentation and tokenization are the same thing, right? Yeah, and you don't have to write your own way, okay? For example, Thai people, you can use a PyThai NLP, right? There's already library for you. Chinese, I'm very sure we have 2-3 Chinese students in this class, so feel free to use. Uh, there's a Jiba and Makeup for other language, so definitely check it out, right? But I don't know everything for every language. Vietnam, I'm very sure there's something called for something, yeah. So make sure you check it out, right? And because it's transformer, it's very natural that there's a attention mechanisms inside, right? So here we ask you to experiment with three types of attention. General attention is basically probably what the code already have. Multiplicative attention and additive attention, right? So this part will be a little bit difficult if you don't understand how to create a W and how to put this in the definition forward, right? You have to put this in there. That is this one, multiply this guy, right? How to do that, you guys need to learn, right? You have to learn, and you will also gain a lot of knowledge how this thing really works, right? Because you just listen to me, you understand 20%. You code, you understand 80%. And of course, you have to compare performance, draw a table, and finally, you have to deploy this as a web application. Yes. Restart. Okay. Which one? Yes. So this is basically the table that we want, like what is the loss What is perplexity, validation loss, validation perplexity, right? Yeah, but anyway, what is the most satisfying moment is when you make the app, right? When you actually see that your app is put in your local host, right? So again, we don't demand a lot. We just want a box, and you say ผมไปกินข้าว enter it go to I go eat rice, right? What is I go eat rice in? You're from India, Nepal. What is I go eat rice in Nepal? Mopak takada. Yes. So that is you put mopak takada and then you would say I go eat rice. Okay. You understand? Yeah. So that's so far so good, right? So hopefully you enjoy this one, right? So we are super practical in this class, and I think the practicality of this class is helping everyone to be motivated to learn and get something done instead of just studying all the theory. But I think this class is both theory and practice. Anyone has any questions? You are excited? Finally, you're able to do Google Translate, right? But in a smaller version. Okay, great. Okay. So today, by the way, today there's no break. Okay, because I have to quickly run to AITCC to teach about deep learning lecture. Okay, so I can only teach until 10:10. Okay, around 10:10. So no break today, just okay. So hopefully you guys are fine, but it will finish at 10:10. All right. So today the idea is transformers, and transformer is basically the thing you must know, because transformer is what ChatGPT is made of. It's what all the models in the world currently made of. In computer vision, in natural language processing, in speech recognition, everything is using transformers. Finish. All right. Finish. That's basically it, right? So let me give you a preview, right? Instead of just jumping to the lecture, give you some warm up, right? So this is from my quick preview of transformer. So transformer, of course, you can have encoder. Let's say I go eat rice, right? I'm sorry, Thai people. My Thai is not exactly good, but I'm trying to learn Thai too. So I go eat rice, right? And this guy is encoder, right? And of course, I don't need decoder if I just want to know whether this is a positive sentence or whether this is a Thai language or English, right? Right? So encoder does not output anything. It just try to understand this sentence and give you some targets or label, right? That is the functionality of encoder, right? You can classify whatever you want about this sentence. What you want to know about this? What is the intent, right? So you can have like 50 intents, like eating, hungry, is angry, whatever, right? So that can be also encoder only architecture. What else you can do with encoder? I would say that you can imagine that whatever you want to classify the sentence with, that can be done with encoder only, right? But by the way, this is not transformer only. This is like basic NLP that I'm still in the basic NLP that this is the functionality of encoder. And then, of course, if we want to do something more, we can also always add some decoder on top of it, right? So this is I go eat rice. I think this is grammatically wrong, right? But anyway, we don't care, right? And then we wanted to, during training, we wanted to actually say, I go eat rice, right? So this is like teacher forcing. And so this is during training, right? So decoder, the functionality of decoder is to say something out, right? That is the functionality of the decoder. So by the way, can we only have a decoder only? We can, right? Basically, the language model you guys did in A2 is decoder only. There's no encoder, right? So you have to understand this idea that in NLP, there's three architecture: encoder only, decoder only, and encoder and decoder, right? And encoder only can be mostly for all the classification possibility tasks. Decoder only is mainly for generation, like language modeling. And encoder and decoder is whenever you have a pair of sentence, right? So this is the big picture you must understand, all right? I'm not even talking about transformers yet. This is like how we deal with different tasks, right? So I don't want you to say that, oh, in NLP, there are like 20 plus tasks, paraphrasing, summarization, etc., or Chucky. For each of the tasks, there are specific network. Yeah, yes, but all those specific network can be classified into only three network, three architecture: encoder only, decoder only, and encoder decoder, right? So this is a very big picture that you must understand, right? No matter what. Otherwise, you cannot use anything from Huggingface, right? Because you don't understand this big picture. Okay, great. So this is a quick review of this tree architecture. But now, let's talk about LSTM, right? In LSTM, how does the encoder look like, right? The encoder looks like this, right? Right? And then this guy is connected to this guy. And then this guy is basically connected to something like that. And this guy is connected to this line, correct? Right? This is basically RNN, LSTM, GRU. All the recurrent variants look like this, right? So, and of course, I'm not talking about attention. If you do attention, you can do attention like that, right? You can imagine there's attention. Okay. So that is LSTM, RNN, GRU thing. But now let us think about how does transformer look like, right? So in transformer, I have to redraw. I have to probably take a lot of space, but okay, let me think. I need to be very smart here. If I delete this, you will have no mental mapping, right? Okay, I will draw here, and then you will see clearly what is transformers. By the way, this is still preview, okay? Not yet the real thing. The real, you don't need to take note of everything. Everything I said is already in the slide, but this is like checked directly from Checky Brain. So in a transformer, let's say we just draw both encoder and decoder. So this is transformer, all right? And I should not use pink, right? I should use like, okay, blue. Yep. So okay, we still have Phom Peking King Kao, right? I still have this 4 words, right? And in the decoder, I still have this 4 words, right? And I still want to decode teacher forcing. I can still use teacher forcing. But the key idea is that I don't want to use recurrent neural network because the big problem is too slow, right? So too slow means what? Basically, you have to like one by one, right? And you cannot parallel. Right? Cannot be parallelized, right? So what is the problem? The problem is the good thing is if we can solve this problem intelligence, if we can solve this problem, intelligence can be scaled through more GPU. You have to understand this key fact that we human beings can make as many GPU we want, right? But even though we have so many GPU, if this is damn slow and cannot be parallelized, we cannot utilize all the all the resources we have in the world, right? So Google, Microsoft, they cannot like train a model. It takes like, no matter how many GPU they have, they will still take 10 years to make this, right? But okay, Google have infinite amount of GPU. Microsoft have actually not infinite, right? China and US are fighting over this resources to make GPU, by the way, if you're not aware. But the idea is that if we can parallelize, then the intelligence can be scaled through more GPU, right? That means the more GPU we have, we can make the network smarter and smarter and smarter by enlarging infinitely, right? So this is the key. This is the idea. So the idea is how to parallel. How do we achieve parallelism? How to achieve, right? Parallelism, right? Okay, obviously it should not be like this, go, 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 right? Right? So the idea is very simple. We basically, firstly, we just treat them like, we go back to the basics. We do something like linearly, right? We take the embeddings. Oh, if we don't do recurrency, oh, wait a minute. What is the main purpose of recurrency? Sharing weights, right? Why do we want to share weight? Because we want the previous one and the forward one has some relationship, right? So that's why we share the weight. But now we say we will not share weight. We will not do like this, right? So how do this guy know this guy? How do they know this guy? And how do they know that this guy is the first guy, this guy is the second guy, this guy is the third guy and fourth guy, right? This is a very, very difficult question, but actually what the transformer proposed is something called positional encoding. And even though this term looks very difficult, it's basically some number that represent the order. So it can be 001, 010, 011, 100, etc. Right? So this positional embedding can help the network know that, oh, this guy is the first guy, this guy is the second guy, this guy is the third guy, etc. Right? So we call this positional embedding. The question is, do we fix them or do we make them learnable? What do you guys think? Do we just say the first guy is always have an embedding number called 001, 010, 011, 10? Should it be fixed or learnable? It's much better to be learnable, right? Because we may understand that, oh, this guy is the first guy, right? But maybe if we allow the system to be learned, the system may learn that, oh, the first guy should have this number, right? This number, because when this number multiplied with that number, it gives you a good accuracy, right? So they would know how to say that this guy is the first guy, okay? They would know that the first guy always have a relationship with the third guy because this guy has some word relationship. You understand? They would define by themselves. If you fix that this guy must be 001, 010, then you don't allow the system to learn complex relationship between the order of item with one another, right? There could be a complex relationship with the first guy and the fourth guy, right? You never know, right? So they have to come up with some complex numbers. By the way, for those who may wonder, like, why 3 digits? It's nothing, okay? I love that some students love to confuse, like, why 3 numbers? I just made it up. It could be probably 100 numbers, right? It's embedding. Again, this is positional embedding or positional encoding, whatever you want to call, but this can be 50 numbers, 100 numbers, 300 numbers, right? And I just make it very short, okay? So it's a learnable. So this is a learnable embedding. And what do I mean by learnable embedding? In the what? In the PyTorch is simply nn dot embedding. Understood? You don't even need to think about this. You just nn dot embedding. All right. So now you have an embedding, but the words also have embedding, correct? The words also have embedding. So how do we combine both of them? There are so many ways you can think about. Add them, divide by 2, multiply them. No, you should not multiply. If you multiply them, they will become one number, right? Then it lost everything. So probably add them together. If you add them together, they will be the same shape, then can be used. But when you add them together with some information loss, right? That could be something that you worried about, but eventually, if it's learnable, we hope that when it will learn that how does it add them together such that some information from the word embedding would not be lost, right? Right. So the idea is add with the embedding of the word, right? Which give you the final embedding, right, of the word. Correct? Yep. So this gave you the final embedding. There's nothing here. There's nothing here. Basically, I create something called positional embedding using PyTorch called nn.embedding, right? What is the maximum length I can have in this sentence? Maybe 1,000, right? And each of the embedding, I want 300 sites. Then you just write this code, right? That length, the first item will have this embedding. Second item will have this embedding, right? And then let it learnable. You understand? Yeah. Very, very simple implementations. And then you just add the real embedding of the word. You have a final embedding. That is positional encoded word embedding, you can say. Now, okay, they even though they have some positional information, they don't know each other, right? You still do not create any complex relationship between them, right? Because you may want to understand verb subject agreement. You want to understand subject object agreement. You want to know whenever it's Chucky, it's Harry Potter, it's always about magic, right? How many rules you can learn? Infinite, right? So many complex rules you can learn in this sentence, right? So how do we do this? Firstly, what do you do is you learn, you create, you try to create understanding how this guy is related to each of them, right? And similarly, you try to understand this guy related to this guy, how much? Basically attention, right? And similarly, you create this guy, right? And then finally, you do this, right? So this process is called, this process of dot product each other is called self-attention. Self-attention, right? So by attending to each other, you get some numbers, right? Now, I don't want to only do this one time because I need to understand that, okay, this guy, the relationship between this guy and this guy and this guy is like, this guy is the work of this guy, potentially the object of this guy is potentially the adjective that describe this guy, right? But sometimes I also want to learn that in another sense, who is this guy talking to, right? So maybe I want to say this guy is always talking with the third guy, right? So you can see that there are different ways I can see this sentence, not only one way, right? So later on in the slides I gave you, I will introduce that actually we don't do this only one time. We can do this something called 8 times, right? Basically, it's like fully connected. You do this multiple times, right? Same thing, but every time you do the same thing, it learns different things, we hope, right? And then finally, all this attention will be sent to the decoder, and the decoder will have exactly the same architecture and do this self-attention thing. And finally, it can decode very well, right? Of course, this part is still a little bit confusing, but once I show you how it operates in the equation part, you understand it very clearly. Um, you may say that, Jackie, why this guy is can be parallelized, right? Because you can see that no one is waiting for anyone, right? Every attention can be done independently. They don't need to wait for anyone. For example, the green line can be in one GPU, the blue line can be in another GPU, the 8 times can be in 8 different GPU, right? So you can see that everything can be done scaled infinitely, right? No one is waiting for anyone, right? But at one point they need to be integrated, the results, right? And then sent to the decoder for the answers, right? But of course, there's still a lot of information that I have left out, but this is like a preview of transformers. Great. So let's move on. By the way, because some students just came, I will have no break today because I have to quickly run to AITCC to teach about deep learning. So no break today, but this class will probably end at 10:10. Okay, just for your information. All right. So that is a preview. I guess 10 minutes preview. So we are here. Transformers. All right, and I will skip here. Okay. Okay, so this is a beautiful picture that is copyright by me, all right? And I draw this myself, and everything probably is nicely drawn. Probably no errors at all, but let's start from the beginning, all right? All right, so in the beginning, we only had the input word embeddings and the positional embeddings, all right? They add up together, all right? And X, the big X, the shape is a sequence length, and embed them, right? Embed them in this equation T and D, right? T and D. Right, so that is X, right? Now what about P? Well, we can initialize using NN.embedding, and then we can say that P is simply sequence length also, and embed them. And this is can be randomly initialized, right? And then finally, the real X is basically just plus them, just add them together, right? Nothing crucial here. So how do we get this positional embedding? If you want to just skip, you just use NN.embedding, all right? But if you want to know the history, I can tell you the history. Here is like the thought process, like why not use the range of 0 to 1? So for example, if I have Harry is flying, right? I can do something like this 0, 0.5, 1, correct? Right? Or maybe if I have flying on his bloom, then I can be like 0.2, 0.4, 0.6, 0.8, right? Right? I can do this. Yep, I can do this, right? But you can see that it's inconsistent if you don't already see, right? The second guy is always changing. right? So it doesn't make sense, right? So scientists drop that. Trust me, no genius, even genius, can suddenly come up with this. I teach you like it's magic. But what is important is not that people can come up with this, it's how people think. Right? You guys, if you guys want to be smart, you need to think like this. Think from the easiest way. Why not this? Oh, cannot? Then what? Then cannot. Cannot. Oh, this can. Finish. Right? This is the what smart people do. But not smart people, just listen to here. Okay, good. Use, right? Then you will never able to solve any problem. So now, the next step is numbering, right? So numbering looks very like super makes sense, right? Like Harry is flying, right? I can simply say 1, 2, 3, right? So what do you guys think? 1, 2, 3 makes a lot of sense, right? 1, 2, 3, right? But the question is, you may not have embeddings for some. You still need to specify some length, right? So that is not so uh, uh, useful, right? The next one is sine cos wave. I will save you from understand this picture, but I will teach you in a very, very simple idea. And for those who want to like really seriously go to, I run from 0 to t, and d is basically, if I'm not wrong, d is dimension, okay? But anyway, very easily said, I can create let's say a sine wave, okay? A sine wave. And I can also create uh, a cosine wave, right? And I also can create okay, let's say that's it, right? But anyway, let's say this is a position 1, position 2, position 3, and this is I, right? So I can create so many sine wave and cosine wave, right? And you can imagine there's so many wave here, right? According to the I wave I have, right? So let's say if I want embedding them to be 300, I will have 300 waves, okay? So you can imagine some wave look like this, right? So I have 300 waves like this. How do I generate this? I just generate using this function. So what is the embedding for number 1? For number 1 is simply take this number, this number, this number, and this number. Understood? So if you have 300 numbers, you will have 300 numbers here. And what is the vector that represents number 2? Well, you just take the unique number that is generated by this unique wave. By having 300 sine cos wave that oscillate in different frequency, you are guaranteed to have unique vectors for each of them, correct? Because you generate using some kind of functions, and you have so many waves represented by 300 waves, right? So this is the initial idea proposed in the 2017 papers, right? And people thought that, okay, it's pretty cool, but this is fixed, correct? This is fixed. The only thing this guy saw is he doesn't want to use 0, 1, 2, 3. So he just say that, can we create a unique number that can represent 1, a unique number that can create unique vectors, sorry, to represent 2, etc. And the answer is yes, using a different oscillating sine and cosine wave, but it's fixed, right? So the question is, can we improve that? And people learn that, hey guys, 2017 paper, actually you don't need to create this complex sine cos. Actually, by the way, even though this sounds so difficult, it's nothing. If you understand sine cos wave, it's just sine cos wave. It's nothing. Okay. But anyway, people learn that no, this way is no one use anymore. Like you don't need to understand this one if you are too lazy, right? You don't need to understand this one. Basically, long story short, everyone just NN dot embedding. Okay, just create a NN dot embedding and just randomly initialize. You may say, huh? Randomly initialize? How do you? Then how do the network know this guy is the first guy? You don't need to care. You don't need to care. Again, if you're still asking this question, you don't understand backpropagation, right? You will let the backpropagation figure it out, forward, backward, right? You will learn that this is the first guy, right? We don't have to think that much, right? So that is the idea, right? Okay. So basically, so here I just say that simply using linear layers, basically NN dot embedding, right? And it's learnable, right? But still, there's a problem that you have to specify the T, right? But still, I guess currently no one solved this problem. Every network has something called max token. All right, you go Huggingface. Every Huggingface model has something called max token. It does not allow infinite amount of tokens, right? And this is the reason, because you cannot have embedding for 10 million length. Cannot. So there's always maximum tokens specified for the position embedding. All right. So this is only this guy. The next guy is multi-head attention. And this word sounds very difficult, but if you already understand my preview, this is not difficult. It's basically you trying to understand yourself many times, right? So first of all, you got your X, right? You got your X. You need to duplicate yourself 3 times. Okay, you will later on know why. Okay. So Q is basically X times some W. K is just your X projected to some W, and V is simply X projected to some W, right? So you can imagine that they are basically Russia copy 3 times, but each of them are a little bit perturbed because they are multiplied with some W. Understood? So maybe this is a Jedi, this is her dark side, and this is her mother figure, something like that, right? So there are 3 versions of her. You understand? And this is exactly this thing. For those who like for those who like to code, that's why I put this for you. If you don't have this, you cannot code. So T is sequence length, and D is embed dim. Okay, yeah, just for you. This is very important for those who code. And then later on, you would realize that whenever you read paper, they always say this, because if you don't give this, cannot code. Okay, great. So everything makes sense. So now, what is the next? This step easy, right? Easy. Next step is you need to create this Q many version. All right. So this step slightly confusing, but still W. Q1 is so we say that no, we're not gonna do something like this. By the way, actually we don't do like this. All right. What we do is we do Q1 is basically equal to X times W. This W will change D to DK. All right, D to DK. So for example, if D is 300 And then the dk, if I have 3, then the dk is 100. Understood? Each of them have equal proportion, right? But the d, if d is 300 and I have 3, then dk is 100. They are basically divided by the number of q you want. So here, if I have 3, I call this 3 heads. I can have how many heads? No one can control. You can do 8 heads. You can have 16 heads. You can have 24 heads, right? No matter, you can infinitely multiply. I mean, you can have so many Q1, Q2 until Q24. But the more you have, if you have 24, you divide 300 by 24, right? If you have 16, you divide by 16. If you have 8, you divide by 8. You understand? But because your D is 300, you need to pick the number of heads that can be divisible. Otherwise, you get digits. Embedding dim cannot be digits. So 300 can be divided by, I don't think it can be divided by 24, right? Then you need to find the number of heads that can be divisible. All right. So now let's say I have 3 heads. 3 heads, right? So because I have 3 heads, Q1, Q2, Q3, my D, let's say, is 300, right? Don't ask me why 300 is example. Then you get 100, right? 100. So each of them has a dimension of 100. Okay, let me pause a little bit. You may have a lingering question in your brain. Why do we need to divide into heads, right? I think I actually preview said already, but basically I want to, you need to imagine these 3 ladies have some complex relationships, right? If I just create one version of them, maybe I have learned that, oh, she likes her, she doesn't like her, okay? This is one. If I only have one version of 3 of them, I can only learn one relationship, right? But this is not true. In this world, each of the word has different relationship with different words, right? In different angle, right? In another angle, she and she come from the same country. She and she come from different countries. You see, same input, but different angle. Do you understand? Similarly, Harry is flying on his balloon. Harry loves to fly, right? This is one relationship. Harry is always carrying his balloon. Harry and Bloom have some relationship, right? Right. So you can see that one thing can have different relationships depending on how you look, right? So if you only create one version itself, you can only learn one relationship, right? So my proposal is duplicate them into 3 or 24 versions of themselves, right? Each of them is a mini version of them. Why is mini? Why do we need to divide, by the way? This is simply because we don't want to waste all the power in the world, right? So we just divide. So this is just purely about computation power, right? So hopefully you understand why do we need to use something called heads, right? It's simply divided them into different versions of themselves, right? Great. So far still very, very good, right? So we have a lot of W's that make them into different versions of them. Now, what do we do? Before I talk about this, how do I know the relationships between her and her, her and her, and her and her, and her and her, right? Very simple, dot product, right? If she is Russia, if she is Q, and T is K, then dot product, right? So dot product. Just dot product, right? Just dot product. Ah, wait a minute. She dot product with she, and she dot product with she. Same or not? Actually, theoretically, yes, but actually, no. In this proposal, we say that we should treat them different way. Whenever she is Q, each of you have can be QKV, right? Whenever she is Q and she dot with you as a K, maybe different new relationship, right? How you look at her, right? At the same time, when you are Q, you can also look at her in different way, right? So you itself can have QKV. So that's why you cannot simply that if you dot product, it's finished, right? So this is a very, very crucial point that you have to think about. Do you guys understand? No. Okay, great. Let me just quickly explain that, right? Otherwise, so firstly, you have to imagine that this X contains every guy, right? All the words, all the four. If I have 4 words, then the X this X has 4 words, right? Right. But this 4 words actually I create a Q1, but this Q1 actually contains 4 words, right? Right. So you can imagine that if I say ผมไปกินข้าว right? And this guy is the whole X, right? This guy is the whole X. What I do is I create a version of Q that the size is also 4, and I create itself that is K, and I also have 4 guy, and I also have V, and I have 4 guy, right? So Q is when you are the origin of the attention, right? K is when you are the receiving end of the attention, and V is basically the final value of the thing, right? So you create yourself 3 times, right? And this guy, whenever this Q dot product with K, you can imagine that this guy is actually dot with this guy, right? This guy is dot with this guy. This guy is dot with this guy. This guy is dot with this guy. You see? This is Russia with T, Russia with me, Russia with Dipali, Russia with, right? But next is T. T will dot with Russia. T will dot with me. T will dot with herself. T will dot with Dipali. The next is, I'm not sure. You can see what I'm trying to say is that you dot with you is not the same as you dot with you, okay? Each of you have QKV. Each of you have QKV, okay? You don't have only Q or you don't have only K. Each of the word has QKV. So why do we have so many QKV? Simply Q is like whenever you are the beginning of the attention, what is the relationship with you and K, right? And K is basically when you are the receiving end of the attention, right? And V is the final value, right? So what is attention I? Attention I is simply you dot product of the Q vector I and K vector I, of course transpose, and then softmax is nothing. You don't have to worry about softmax. Softmax just make everything 0 to 1, right? Nothing. And divided by square root of dk. If here is 100, then just divided by 10, right? Nothing. Why do we need to have this? Just to make numbers small, okay? Otherwise, your gradient is very big. Make gradient small, right? And then finally, you multiply that attention with vi, right? Which is a really the attention that you attend to K and multiply with yourself again, right? So that you know, okay, my relationship with K, that is how much, and I multiply with myself. I would know how much I should attend to that, right? So that's attention I. Okay. Of course, currently you may probably understand like 10 to 20%, but once you go coding, you understand truly everything I taught. The only thing you need to understand currently is there are so many heads. Why so many heads? And you also need to understand that each of the word has QKV, and Q dot K and K each of you have Q and K, right? So it's not bidirectional. Great. All right, so this is attention. And finally, this attention can be concatenated, right? Can be concatenated. So this attention originally is decay. So you concat them, you multiply with a weight WO. Why you want to multiply with a weight WO? To combine them into D, which is 300, right? In this example, right? So you just multiply with a W to project them back into 300, right? So that is the multi-head attention, right? That is probably the only thing you need to understand in transformer. Other thing is not difficult. Like other thing is linear layer, linear, okay? So that is the only part you need to understand. And maybe I can have some time to show you the code and you probably understand better, right? So what do I do next? Once I do the attention, I do some addition. Right? So firstly, okay. So firstly, what I do is I got some output here, right? Right, from the previous layer, right? Which is QKV divided by under square root of dk. I add them with this guy. What is this guy? This guy is x. Okay, so you add this guy here. Well, Chuck, you already transform each of them into QKV. Why you need to add this guy back on? Well, this technique is called skip connection. And there's a lot of theory behind, but long story short, by adding this x here and add them to whatever the attention is attended, you allow the system to choose, Chucky, all this attention that you learn is useless. Actually, you can use some of the original x already and can be used in the next layer. You don't even need to learn the relationship that that's not like her, right? Or she like her, because it's not necessary for prediction, blah, 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 okay? So by adding the original x to the attention, you allow the model to say that, hey, this part of x useful, this part of x no useful, this part of attention no useful. I just use the original x, combination of them, right? You can then use it for prediction, right? You don't throw away the original x because you can see this. If I do so many layers, like infinite amount of layers, I do this so many times, right? Maybe this part is doing no use, right? It's doing 50 times already. Maybe this guy no need to do already, right? But because I force it to do, it learn useless thing. It learns something like noise, right? I don't want that, right? So this mechanism allow me to say that, oh, Chucky, if the computers learn that, oh, you passed through this 50 times already, maybe you don't even need this, right? Then the computer will learn, just learn an identity function, right? What do I mean by identity function? Like you and you attention 0, you and you attention 0. Understood? Like there's no attention between you and anymore, right? Then whenever you add them, x, the output here will always be x. Then you don't need to learn anything. So this is a very useful technique to say that if you learn many times like this, you allow the computers to say that you stop learning already. All the attention you learn is already enough already. So you can skip, right? And then you will eventually learn that this guy is basically an identity function, right? So that is a very short version of skip connection. But anyway, once you add, what do? You normalize. You normalize. And I don't even need to think about, I don't need to teach you how to normalize, right? You just yourself minus mean divided by standard deviation, okay? It's like basic normalization, right? Great. By the way, there's a batch norm, layer norm, instance norm. Of course, it's confusing. You go look, batch norm is across batches, layer is across sample, across dimension, and instance norm is across each of the sample, if I'm not wrong. But I say so quickly, you guys just check, okay? There's a batch norm, layer norm, instance norm. But okay, let me be quick. Batch norm usually used in image. Layer norm is usually used in NLP, okay? In short, yes. Okay, now the rest is again nothing. You pass through the feed forward. Feed forward is linear layer, okay? So, and then you skip again and add a layer norm, right? So feed forward is basically you take the x, multiply with w1 plus b1, and then there's a max. This one is simply for those who like, what is this guy? This is basically ReLU. So you pass through a linear layer, you go to ReLU, and you can multiply it with another W, okay? So basically, okay, for those who are comfortable with PyTorch, it's basically and the linear, and then the ReLU, and then the linear, okay? This is what this guy is. Yep. For those who are like, what are you doing here? Okay. And okay, so you already understand. If you, by the way, if you understand this purple thing, you already understand transformer. Transformer, there's nothing else than here. And here already clear like a lot of the myth behind like, oh, transformer is so difficult to understand. Actually, it's only 2-3 equations, right? And there's nothing. And I told you already in machine learning class, if you understand linear regression, remember, you understand basically everything. Is this is not more than linear regression, right? But it's just super aggressive linear regression, right? Like crazily a lot of linear regression. Right? But anyway, now let's come to the decoder, right? So in the decoder, we do the same, right? We take the output word embeddings. I go eat rice, add the position embedding, duplicate itself 3 times, QKV, do the mass multi-head attention. What do I mean by mass multi-head attention? Usually when you do attention, this is how does it look, right? So if you have each of the word here, deep learning is fun, deep learning is fun, you will have an attention number, right? What is the attention between deep and start, right? This could be like, so this can be the Q and this can be the K, right? So Q, K, maybe 50, I don't know. Deep and deep maybe like 100, like so strong because they are the same word. Whenever deep is Q and learning is K, maybe I don't know. I just, right? You can imagine some number, right? And whenever learning is Q and whenever this guy is K, I don't know. But they are not bidirectional, by the way. Okay, they are not bidirectional. You cannot say that the half triangle is the same as bottom triangle. Okay, not the same. Now, okay, let's say you have full table, right? You will have full table here, right? You will have a full table here. And when you have a full table here, you just multiply with V, right? Right? You use this full table, multiply with V, you will get the output, right? That is the basic idea of that multi-head attention. But in decoder, you cannot let it have attention in the future word. All right? Why? Because you train it to predict the next word, right? If it already know what is the next word, it does not need to learn anything. It always answer the next word, right? It already know the answer, right? So you don't allow them to pay any attention to the future word. So basically, how do you do? Super easy. You may compute everything first. Once you compute everything, you just set everything here minus infinity. Okay, that means no attention. Okay, no attention. Yes. Yep. Why minus infinity? I think your question is why not 0, right? 0 Oh, okay. Plus infinity is not good. Plus infinity means I should pay super, super, super high attention to this guy. Yeah. Minus means I don't like you. Bye bye. Like bye bye. Okay. And I don't care about you. Okay. This is what this minus infinity means. Bye bye. Huh? Zero means that zero is still better than minus 0.1. Correct? Correct? You understand? So zero is not a good number. I don't like you, but I still have a little bit feeling for you, right? But minus infinity is bye-bye. You understand? Bye-bye. So zero is not the right number because zero is still better than minus 0.1. You understand? Yeah. So that is the idea. So how to do this? Don't worry. Chucky wrote all the code for you already, right? So later on, I have only 10 more minutes, all right? But anyway, it's already finished. Yeah. And once you see the code, you understand almost everything. So now, where does the information from the encoder flow in? Here. The output from the encoder will be duplicated. You can imagine that this guy is X, okay? It will be duplicated 2 times as what? As you need to see the arrow clearly as K and B. Okay? And then Q comes from the decoder. Okay? So here you need to understand that, okay, here QKV come from the decoder, but here K and V come from the encoder, Q come from the decoder. Understood? So this is a little bit information. So Chucky, is there any way I can remember this? I don't want to memorize. Actually, yes, right? Because I don't know how you guys will remember this, but basically you can imagine that this guy is the Q. This guy is the question. This guy is like, I want to, there's a question posed here, and I want to know which of the words here I need to pay attention to answer this, right? So this guy is a question, is the guy that I want to put here, and I want to pay attention. Q, which K here, right? It could, here is the K, right? ผมไปกินข้าว right? And Q could be I go eat rice. I go eat, right? So this guy is a Q. I want to know how much to decode I using the information POM, right? How much to decode go for each of them, right? So this guy is K, this guy is Q, right? And V is also this guy because I want to use this embedding to help me decode this one, right? So that is the way you can actually memorize. How do we? Why do K and V come from here and Q comes from here? And then finally feed forward nothing, linear layer, add layer none, nothing, linear layer, nothing, softmax, nothing, output probability, nothing, right? If you code, you say nothing because it's in and out linear and then a softmax, right? So yep. Those are the information for transformers. Okay. I will not show you the results because just say that transformer is so super good. Okay. But the next thing I want to show you is the coding. It's right here, DL, SIG to SIG, and yep, transformer teacher forcing. Yep. All right. So this code, I can say that it takes probably a lot of time to write this, but I enjoy a lot. So this is the real picture from the from the paper, right? So you take the inputs, get the input embedding, add together with the position embedding, do multi-head QKV, multi-head attention, and a norm, blah, 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 right? You can see K and V come from here. Q come from here, okay? Everything look the same, right? But I will quickly tell you how I code, right? Don't worry, because your A3 is this guy. Yeah. Guys, yep, I think you will enjoy my code. This guy is just the encoder. This guy is just the encoder. Encoder is basically whole thing, okay? But the real guy is here, encoder layer. Each of them is like this, right? So you can see that my I'm not sure at the back you guys can see, but in the forward I have self attention, and you can see what I put, sauce. Okay, this is basically XXX. Okay, and of course some mask. This mask is for padding. I don't want it to pay attention to padding. Okay, so this is for padding, sauce mask. But sauce is QKV. Okay, you remember, okay? Self attention is QKV. And then later on, after I do self attention, I do layer norm, right? But before I do a layer norm, you can see there's a skip connection. Source, here's the skip connection. The original X is here, plus some drop out, and then layer norm. See, this guy is a cell skip connection. Do you see? This is skip connection, okay? No fancy code, it's just plus, okay? And source is from the original input, right? And then finally, position feed forward. This word sounds so difficult, but just two linear layer. And then again, layer norm again. Skip connection again. See, nothing, right? So this is the encoder. Check it. This you are oversimplifying things. You are not showing each of the function. I will show now. All right. Let's go to the self attention. This guy loves to write, right? You can skip him. So now, firstly, you need to check. I have WQ is a linear layer. I have WK is a linear layer. I have WV is a linear layer. Okay, very simple. Nothing. And I also have another WO. This is like finally when they do all the attention combined together. Okay, and this is for the divided by square root dk. Remember, this guy is a square root dk. Okay, finish. So do you guys remember sauce? Just now I say sauce, right? I changed the name. I changed to Q value, and I just say Q is WX, K is WX, V is WX. Okay, nothing. The code is like there's nothing, right? Very simple. Here is the part that I chop them into heads. All right. So this is like a little bit complicated, but actually no. I just use reshape. You know reshape? You guys know reshape, right? Change the shape. I just say that instead of let me show you clearly. I think I can go like 15, okay, or 20. Don't worry, I can run. I can run with. I think some of you are still need to also go to AITCC. Yeah, here. This guy is D, right? Correct? This guy is D. This guy, let's say this guy is 300, right? The idea is I just reshape them to this two guy. So what is my head beam? Let's say my head beam is, I don't know. I don't know my code. I mean, it doesn't matter what is the dimension. I can say that 3 and 400, right? Then I just say reshape whatever rest of the input put here, but I want to change this guy to 3 and 100, okay? Then you already have 3 QI. You understand? Yeah, so now you have 3 of them, each of them 100. Okay, so this is like a very simple technique to you to get 3 heads. If you want 8 heads, you just put 8, right? But here, if you 8 cannot be divisible, right? The PyTorch will say bye-bye. So you need to 300 divided by 8 cannot, right? 6. 6. Then is you can use 6 and then 50, right? Something like that. You can also do like this. How many? You may ask me, Chucky, how many heads is beyond my capability to answer that? Is because there's a lot of experiment, right? But typically people use 8, right? In BERT, 16, 24. In ChatGPT, 50, 100, right? Okay, so no need to talk about. Okay, so the QKB. You see, very simple. You understand the theory, and then you come to code. You understand better, and then the rest is a piece of, no, it's manageable. Yeah. Now energy. Why is automatically moving? Okay. This guy is QK divided by square root dk. See, it's already here. Chucky, the only part that is so difficult is how do you know you need to reach permute? This is simply transpose. Okay, this is simply transpose. And softmax is right here. Okay, softmax is right here. And then finally, you need to multiply with V. You multiply with V here. That's it. You don't need to do this so many times. You just do one time because they are already a matrix, right? You just boom, you already do for everything, right? And then yeah, the rest is just rearranging them to be in the proper format, right? Okay, hopefully, if you understand this part, you already understand transformer. Okay, other part is there's no. I really want to tell you that it's not difficult. There's also FCO here. Chucky, you told me when you do multi-head, you need to concat, right? Where's the concatenation? Here, because this is the original one, right? Once you reshape, it's automatically concat. Okay, you don't need to say concat because you have 3 of them, right? You just say this, right? And it's already concat. No need to concat. And then you just pass through some FCO. Even though it's hit them, you transform them into maybe another transformation version, right? And then send to them, right? This is the only part that is difficult. The rest is there's nothing in transform, and hopefully you'll realize that. Okay, so for those who are wondering like what is feed forward, linear, okay? So you just do linear ReLU, drop out linear, okay? Chucky, why 2 linear, why not 3, why not 4? I just follow the paper, okay? Trust me, the paper also don't know. They just try 2, 3, 4, they find that 2 is the best, okay? So the decoder, of course, I need to talk about the mass, but maybe the decoder is nothing, okay? The decoder again is not the real one. The decoder is the whole thing, okay? What you need to pay attention is the decoder layer, right? And in the decoder layer, right, you can see that again it go to the same guy, target, see, and then QKV, blah blah blah, and then the skip connection, and then you need to get the encoder attention, and then here you will see already. Here, the target is Q. Anything come from encoder is K and V. Remember? Remember? K and V come from encoder. Q come from the decoder. Yes. Yep. And then the layer norm, blah, 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 blah. Yep. And putting them together. This is the mass, right? Okay, that's one thing I need to tell you. So how do we create this mass? First of all, this mass is simply using this function. Okay, this function is called triangle left or something. I don't remember, like top triangle or something. And then it will automatically just set everything to like that number. Okay, so this is the function. You don't have to worry. Very simple, right? But now, something that I need to pay attention is you also need to do padding, right? So even though this is the target mass, because we realize that this token is actually a padding, we also need to make it 0. So this is like the target mass plus the source mass. If you don't understand, don't worry. I spoke everything in the YouTube, right? I spoke very calmly. I wake up, drank my coffee, and explain to you every step. Okay, so that if I speak too quickly now, you go watch my YouTube, right? And everything is the whole function is nothing. Encoder, decoder, finish. If you understand, then you go look at what is encoder and decoder, and basically that's is for the whole thing. And the training is nothing. Like it's basically the same code that you guys already know, like evaluate, blah blah blah. And okay, Chucky already gave you all the code to compute complexity. You don't need to do anything. Chucky already wrote. You see, I'm very kind. My assignment, my only thing I want you to do assignment is I want you to find some data set about your country, load it. How to load? You need to learn. How to tokenize your language? You need to learn. But that's it. That's the only 2 things I actually asked you in A3. The rest, I want you to read my code and understand my code. Okay, great. I have to catch up. I have to run. But thank you very much and see you next Monday. Bye-bye.